In this video, I am going to discuss gravity assist and the orbital reversal maneuver. This is from the Appendix C of the book. You can buy the book by just scanning the QR code, which is like just below. Okay, so gravity assist is it's like almost seems like magic because normally when you think of a spacecraft and it's approaching a planet, so it falls into the planet's gravity well, and then you think that okay, if the spacecraft wanted to exit, it'll have to burn fuel, so it is going to lose velocity when it exits the gravity well. However, falling into the gravity well of a planet can actually increase your velocity of the spacecraft. When it exits, it'll have a greater velocity than it started out with. And also, if you burn fuel while you're in the gravity well, you'll get more velocity for the same amount of fuel, and that's the Abridged effect. But in this video, I'm just going to talk about gravity assist. Okay. Now, so gravity assist is a maneuver, and it uses the gravity of a planet or other celestial body to alter the path, which can also be very useful if you can change the direction and change the velocity of a spacecraft. It can be used to accelerate or decelerate a spacecraft. And why would you like to decelerate a spacecraft? Well, if you're sending a spacecraft, when it reaches the destination, you need to slow down to just make a landing at the destination, or if you want to do an orbit around a particular celestial body, you may need to slow down. And to do that, you can either burn fuel or you can use gravity assist to slow down your spacecraft. So both accelerating and decelerating require fuel, unless you're, of course, using gravity assist, which can be helpful. Okay, so I actually, when I was writing the book, I was kind of like trying to calculate how long it would take to get to Alpha Centauri, and one of the things I realized is that gravity assist can actually give a huge boost to the speed of the spacecraft and thus cut down the time taken to reach your destination. And I couldn't really find any good source of understanding gravity assist, something which can be explained in like 3-4 pages. And so what I finally did is, I taken my engineering entrance exam when I was 17 years old. And so I did remember, like, I remember mechanics and I remember calculus. And I also did a couple of courses in engineering, in mechanics and calculus while I was studying engineering. So anyway, I had to figure it out myself. I did not really get any good source. I'm sure there are lots of sources. I could have bought a textbook and I could have gone through like 100 pages, but I didn't want to do that. I wanted to kind of get to the point. And So I figured out this gravity assist and I also put it in my book. Okay, so when you think of gravity assist and um, you are actually the first thing to start with is an understanding of Keplerian orbits. When a spacecraft or an asteroid or something approaches a celestial body, which could be a planet or a star, and assuming that the mass of whatever is approaching is much smaller than the celestial body, it can have different kinds of orbits. Uh, if it is what is called captured by the celestial body, then it will have an elliptical orbit, which is this red orbit that you see. Somewhere between being captured and not captured is this like a green orbit, which is a parabola. And so this is like the boundary of being captured. So even a parabola is unbound, so it will not actually orbit the celestial body, but it will keep going away. And the hyperbola is when it is not captured and it just experiences a change in direction, and it may experience a change in velocity. You have to understand about inertial frames of reference. Now, an inertial frame of reference is a frame of reference in which Newtonian classical mechanics applies. And interestingly, you can have I am right now, let's say I'm in a frame of reference. I'm sitting on my chair, I'm waving my hands, I'm applying force to move around, nod my head, blah, blah, blah. Okay, so, and all this can be analyzed in this inertial frame of reference in which my room is stationary. So you can say the room is the inertial frame of reference. Of course, the Earth is moving at a velocity, and my room is sort of in the same frame of reference as the Earth. But the Earth is moving with respect to the Sun, and if you're approximating that it's moving in a straight line, it's actually moving in an ellipse, but approximate it's a straight line, then the Earth has a particular inertial frame of reference which is different from the solar inertial frame of reference. So when you have an inertial frame of reference, you can apply the laws of motion, the Newtonian laws of motion to it. For example, one example of it, like suppose you're in a plane and the plane is like flying at like 1,000 kilometers an hour. And you're playing ping pong, also called table tennis. So there's a table tennis table in the plane, and you're playing table tennis with your friend. You will not be able to make out any difference in the game, as even though the plane is flying at a very high speed, it would like appear to you just you're playing like on the ground, as long as the plane does not accelerate or decelerate. So as long as the velocity does not change, so you're in the inertial frame of reference of the plane, and you can't, and everything works the way it would work, like suppose you are on Earth. So the point is that the laws of motion apply unchanged in an inertial frame of reference. It does not matter how much velocity that inertial frame of reference has with other inertial frames of reference. So what you do know is that what are you going to use for gravity assist? The one thing that you're going to use is that in an inertial frame of reference in which the celestial body is stationary. So you can say it's, let's say it's a planet. So in the planet inertial frame of reference, the orbit of whatever the spacecraft is going to be either a parabola or a hyperbola, assuming that is it is not captured by the planet. Okay, and the planet, of course, is in an orbit around the sun, but you can, for the purposes of gravity assist, you can just assume that it has a uniform rectilinear motion in the solar frame of reference, which is referred to as IFRS, in which case you can uh, define a new inertial frame of reference, which is the planet in which the planet is stationary. So I'm going to call that inertial frame of reference IFRP. P is for planet, S was for solar. Then let's take a look. So here we are, and we have a planet here, which was actually going in this direction in the solar inertial frame of reference. But moving on to the planet frame of reference, this planet is stationary. And if this planet is stationary and you have a spacecraft approach it along this line and then get deflected, so its actual path will not, of course, be straight lines because it will be slightly curved. But I'm just approximating it, drawing. I'm just kind of continuing the asymptotes, and then the point where they meet is the center of the hyperbola. So what you have by moving to the inertial frame of reference of the planet is that you have the path of the spacecraft, and which you know is a hyperbola. So let us say that initially the path of the spacecraft, the asymptotic path, was at an angle theta with the direction with x-axis, and x-axis is the direction of motion of the planet. Of course, in the inertial frame of reference of the planet, the motion of the planet is actually zero. So let's say it was at theta, and then after passing by the planet and having its direction change, the direction is phi. You have to, there's a certain amount of, shortcut you can use. Let's say you know that it's a hyperbola, so you can avoid the calculus, but you still have to be precise. You have to be precise about everything you say. Otherwise, classical mechanics explains a lot of things. It is very precise, but it's also very unforgiving. You can't make any mistakes in setting it up. Now, with all this, you can next set up the equations, and the details are in the book. So I'm just going to kind of skim over this, and what you get is that the initial velocity along the x-axis is given by this formula, and the final velocities along the x and y axis will be given by these formulas. One common way to think of it is you throw a ball at a cricket or a baseball bat, and the bat hits the ball, and then the ball speeds up. So if a ball is coming in and the bat is also, they're approaching each other, after collision, the ball is going to rebound and go off at a greater velocity, and the velocity is going to be greater the greater is the speed of the bat. So you can look at it from a, and the change in velocity is going to be greater if the impact is elastic. And because in the elastic collision, there is no energy wasted as heat. Now, the question is that gravity assist is actually an elastic collision. It is very similar to an elastic collision. And thinking, but there was no collision. It just sort of swung by, right? Now I'm going to show you where the collision actually occurs. So you have the spacecraft which is coming in, and then it's kind of being attracted by the planet, so it's sort of speeding up. And then once it gets behind, this planet is now, the spacecraft is actually now being pulled in this direction by the planet, right? Just like when a bat hits the ball is given a force in its opposite motion, direction of motion, of its initial motion. Similarly, the spacecraft in like all these points experiences a gravitational force which is going to make it accelerate in this direction. So that is the, sort of like a collision, but because they never touch each other, there is no energy wasted as heat. So it is like a elastic collision. And of course, because the distance when it is in this part of the orbit, this distance is a lot less than, let's say, this distance or this distance. So the force is also, it may seem like this is like a small part of the orbit where the spacecraft experienced a force which had a component in this direction, but because the distance was less and the force increases as is inversely proportional to the square of the distance. So there's a considerable amount of force. And so this is like it is analogous to the spacecraft being smacked by the planet and being deflected and going off in the other direction. So I just sort of crunched the numbers. I call this the orbital reversal gravity assist maneuver. And the idea here is that, let's say you assemble a spacecraft at, let's say near the Hector asteroid or Jupiter or somewhere. So like, more towards the outside part of the solar system. You assemble it. And then if you reverse this direction of motion, so then it's going to come down. And then it's going to, if this is the orbit of Venus, then it's like 2 is the orbit of Venus. So it's going to approach Venus in the other direction from which Venus is traveling. And just like a ball when it's hit by a bat, if they're traveling in different directions, you're going to get the ball is going to experience an increase in velocity. And that is what the goal is, to increase the velocity of the spacecraft so that it can get to its destination faster. Now, what happens if the ball and the bat were moving the same direction? Well, that's what is called bunting in baseball. Bunting, the batter really wants to slow the ball down and just wants to make it drop. So when the ball is coming in, the batter does not go forward to meet the ball with his bat. What he does is he starts withdrawing the bat, and then the ball hits the bat and then sort of like this drops. Same thing here. If the spacecraft and the planet were moving in the same direction during the time of gravity assist, initially if the spacecraft was moving the same direction as the planet, then there's likely to be a fall in velocity. Just like when a batter bunts a ball in baseball. Okay. So some other this was actually this spacecraft was assumed to have been assembled from the Jupiter Trojan 624 Hector. Now, why Jupiter Trojan 624 Hector? Right down there. It explains all that in the book. And so if you now 624 Hector is traveling the same direction as Jupiter, is traveling the same direction as Venus. So you actually have to reverse the orbit of Jupiter. Whatever you assemble from Jupiter Trojan 624 Hector, you have to reverse its direction if you to make it instead orbit in this direction if you want to get that gravity assist benefit. And then the question is, okay, instead of going through all this trouble, why not simply take this Jupiter Hector 624 and add that velocity that you would add delta V and send it towards its destination. And then if you do the calculation, what you find is that so after you've done gravity assist also, there is a loss of energy by the time you exit the solar system, because you're moving from the orbit of Venus to a point which you can say approximate to be infinity. So there is an increase in the potential energy of the spacecraft, which is paid by the loss in kinetic energy. And doing all those calculations, what you find is that the spacecraft is going to exit the solar system where its potential energy has gone from negative to approximately zero at a speed of 63.54 kilometers per second. Instead, if you took so you had to use some delta V to reverse the orbit of the spacecraft. Instead, if you just added that delta V to the spacecraft, what you would have at the time of exit from the solar system, only 26.66 kilometers per second. So there's a very significant increase in velocity at which you exit the solar system. And besides velocity, gravity assist can also be very useful in pointing your spacecraft in the right direction. Okay, so like I said, I was going through, I was trying to figure out gravity assist, and I went through a few different sources, and I was a bit surprised why at the amount of mistakes there were. And, basically, I looked at 4 sources, and they were like, I think, because one of the sources actually gets it right.
Okay, this is something that's hardly ever explained, and that's why we have these explainer videos.
Cool.
So here's the answer. It turns out if you approach a planet from behind,
Okay.
there it is orbiting the sun, right? And you approach it from behind in its orbit.
Right.
Not only will the gravity pull you in,
Mm-hmm.
but you will gain speed just to catch up with the planet in its orbit.
That makes sense.
As if you approach a planet from behind, you are very likely to lose velocity. That's just like a ball being bunted. The bat and the ball traveling in the same direction. The planet and the spacecraft, if they're traveling the same direction, then also the impact of gravity assists to reduce the final velocity magnitude of the spacecraft. Moving on to the next one, we have, okay, so this is MIT open source. And here what we see is the professor was calculating the final velocity for the spacecraft. And let's see.
We have VI minus twice gives us a plus the Saturn velocity, and that equals minus gives us a plus the final velocity of the spacecraft. And then we have three minuses here, so that gives us a minus the Saturn velocity. And we know from the problem that the initial velocity here of the spacecraft was actually given at 3 Saturn velocities. So we can tally this up now. We have 3. We have 3 plus 1 is 4, and we'll put this over on the other side. That gives us 5. 5 Saturn velocities equals final velocity. So
okay, the problem here is that the components need to be considered separately. There is an x component and a y component. But the professor is simply adding the velocity magnitudes of the spacecraft to the velocity magnitude of Saturn, even though they are not traveling in the same direction. Okay, the Saturn y component is 0 if we use our diagrams which we had before. And so what you can add is you can add the x component of the spacecraft's velocity to the x component of Saturn's velocity, but you cannot just ignore the y component of the spacecraft's velocity. Okay, let's look at what another reasonably good source of science articles, and that's Wikipedia. What does it have to say? Well, again, here it says to increase speed, the spacecraft approaches the planet in the same direction the planet is orbiting the sun. No, most of the time when you approach it in the same direction, as we saw in our table, you lose velocity and departs in the opposite. To decrease speed, the planet approaches the spacecraft approaches the planet traveling the opposite direction from the planet's orbital velocity. No, this actually increases speed. Let's just edit it. Let me get rid of this error. Okay. And now we have somebody who does get it right, and that is Scott Manley. And he has a very popular YouTube channel,
So yeah, this is a very simple diagram. Now, many of you will immediately get confused because the coordinate system is backwards, and that's because if you look down on the planetary system of the Earth or Kerbin from the North Pole, then the planets move anti-clockwise.
These numbers are correct, and you can plug these his numbers into the equations that I have in my book, and you will get those answers, his answers. Okay. Okay. So